Bon, alors, bienvenue au séminaire d'informatique cognitive. C'est mardi, le 2 janvier, si je ne me trompe pas. Et puis, notre conférencier est Bob McMURRAY de l'Université d'Iowa. Et puis, son sujet, c'est le mythe persistant de la perception catégorielle, de la perspective des origines, de ses origines en perception de la parole. Bob est professeur de sciences psychologiques et cérébrales à l'Université d'Iowa. Il travaille sur la perception de la parole, la reconnaissance des mots en lecture, la façon dont ces compétences linguistiques fondamentales se développent et comment elles varient dans une variété de langues et de déficiences communicatives. Now, what I've done, Bob, is essentially given the essentials of the bio in the talk, and now I'm handing it to you in English with the request that since there are a lot of people, overseas people, and whose English is not their first language, could you speak slowly and clearly?
As long as I can carry a big stick. Thank you, Stephen, for the wonderful French introduction. Never been introduced in French before, and that was cool. Also, thanks for inviting me. This was a really neat opportunity. I was actually first exposed to many of the theoretical issues in categorization at UCAM when I attended the categorization summer school in, I don't know, like 1998. So this is a very fun treat. I'm happy to be here. This is not a usual talk. This is not actually, it really hasn't been my core line of research in a while. But I was invited because of a paper I published, a review paper that really attempted to synthesize a whole lot of work from speech perception and to try to wrestle with this issue that's been we've been discussing since 1957. So in the spirit of this slightly unorthodox talk, which is in many ways more of a lecture than a seminar style presentation, I want to thank my mentors, Dick Aslan and Mike Tannenhouse at the University of Rochester, and Dick, of course, is at Yale now, who really set me off down this road. And I will actually talk about one or two studies we did together. A couple of former students who worked on some of these issues, Joe Toscano, who's at Villanova, Effie Capnula, who is at the Basque Center for Brain and Language, and McCall Serrett, who's about to start a professorship at Gonzaga. And I also want to thank my readers. So like I said, this was instigated by a review paper I recently published in JASN, and I got enormously helpful feedback from Matt Wynn, and particularly Ben Munson, Ethan Kulu, Joan Serino, and Allard Youngman all gave me really interesting ideas, and some of those ideas are going to be here. So I want to kind of thank them. But I think more importantly, I'm really building on work that I did not do, that was done, much of it was before I was born, in particular work by David Bizzoni, Dom Massaro, Joanne Miller, and Sheila Bloomstein, and by Bert Schouten and Ellen Gertz. And I want to acknowledge them right at the beginning because the empirical work I want to present comes in some ways directly from them, and then my own work was very much inspired by them. So categorical perception, in my view, and I guess I'm getting old enough where I get to have a view on this, is probably the single most impactful finding from speech perception. It's the thing that shows up in every single psycholinguistics textbook, every single phonetics textbook. It's probably one of three things that any cognitive psychologist in any field could say they knew about speech, right? The categorical perception, the McGurk effect, and what they would call the cocktail party effect, which is usually not very well defined. But categorical perception is it for me. It's the big one. Well, what is it? Well, I want to start off by pointing out that CP exists really on two levels. And the first level is that it's a very well replicated and robust empirical paradigm. Anybody can do it in the lab. It's well defined. We know how to get it. I'm not disputing the veracity of those findings. It also makes theoretical claims about the nature of perceptual encoding in speech. And we need to think about it in both levels. It's not just a matter of whether this finding replicates or not. It's not just a matter of whether the theory is good or not, but it's how this fits together. So let's start with the empirical paradigm. This is hopefully review for most of you, but Al Liberman and his colleagues at the Hoskins Lab started this by creating a speech continuum. So they took a sound like ba, and they systematically manipulated the acoustics in tiny steps to go from ba to da to ga. And you can see this is the original printout from their paper. They would feed this into the pattern playback machine, and it would create these roboty sounding speech sounds that would gradually transition. And the first thing they asked subjects to do was to classify each token, right? They would hear token 3, and they would say it's a ga or a ba or a da, whatever they thought it was. And when you do that, you get functions. You're going to see a lot of functions that look like this, where you see stimulus value moving along the x-axis, and then you see the percentage of identification on the y. And you can see steps 1, 2, and 3 are almost uniformly identified as ba. There's a very sharp transition, and then steps 5 through 9 are da, sharp transition. Steps 11 through 14 are ga. Now, this is not categorical perception. A lot of people would call it that. They would. You'll see this in talks all the time. You've probably seen this yourself. That you put up an identification curve like this and say, look, we have a categorical perception curve, or look, this is categorical perception. This is only part of the definition of categorical perception. And the first part it offers is that identification has to be, quote, steep. Now, there's a problem with that definition. One is that's completely arbitrary. I could make a very steep categorization function if I used very large step sizes. The other thing is, and I think this is less appreciated by people outside of people who work on this, is that it has to be sigmoidal. There's no other way for this to look. You can't say that something is ba more than 100% of the time. There's no extra credit in a speech categorization experiment. And so it's going to have to asymptote at 100. There's also, I will say, and I discussed this in the paper, there's no way to compare these across continua easily. And nobody ever does adaptive approaches until recently, where you can ask, like, really, how steep is this? So steep identification is sort of part of the classical definition, but it's the weakest link. It's not something that's very easy to quantify. But the other part is, so the other part, and this is really what made Liberman's approach novel, is it predicts categorical perception, predicts a very specific profile of discrimination. So once you do the identification, you can actually find a subject's own boundary. For example, this particular data set, which I think is 4 subjects, these people's boundary was between steps 3 and 4. So all of the ones below 3.5 are ba, above 3.5 are da. So then you can ask, well, what about 2 tokens that are within a category, say steps 1 and 3? Or that span a boundary, say between steps 3 and 5. And categorical perception predicts that you should have poor discrimination within a category and good discrimination between. And this is exactly what Liberman found. If you see over here, the x-axis now is like, where's the center? Where along the continuum are you doing the discrimination? So here at step 1, that's step 1 versus 3. And you can see listeners are at chance. At step 3, however, now they're comparing 3 versus 5. That crosses the boundary, and they're very good. And then once you get back inside the D category, they're no longer very good, and they show a P caret G. Now, the predicted is really an interesting approach, and this is true of categorical perception from the beginning. What Liberman and his colleagues did was they said, let's assume that the only thing listeners know is the label. They know whether a sound is B or D. They have no access to what step number it is. Well, and we know how often they said a sound was B or D. So from that, we can predict whether those 2 sounds can be discriminated and at what rate. And you can see actually a fairly close match until you get to the Gs, where the predicted sort of matches the obtained, the actual discrimination data. So this really suggests, you can think of this as a hypothetical model in which perception is only in terms of labels. And for the most part, that model does a fairly good job of predicting people's performance. All right. So here's a simplified version, just to kind of give us a visualization and see. So here I've actually generated identification data for a voice onset time continuum. Voice onset time is the Q that turns a B into a P. You can see the identification looks like this. Here's the predicted discrimination. The critical thing to see is there's a peak at the boundary. That's the hallmark. Oops. Now, that's the empirical finding. And like I said, that's well replicated and very concrete. Categorical perception also makes theoretical claims about how speech is encoded. And I'm going to kind of lay them out here. And we can debate whether they're true or not, or whether this is even the right framing. What I've got here is a spectrogram of the word ship. And I'm going to work with fricatives a lot today because they're really interesting speech sounds, and I think they're understudied. So you could see at the beginning here, we've got the sh, right? And then you've got the voicing at the end, and I've labeled some things. I've labeled like the first formant and the second formant. If you're not a speech person, you don't need to know what all these are. Suffice to say that phoneticians can look at these and we can measure particular cues, right? So this thing I've marked in yellow, that's the place, the frequency at which there's the most energy. We'll call that the spectral peak. That's a really important cue for distinguishing, say, S from esh. You can hear sh is lower than s. You could measure the duration. You could measure the frequency of these energy bands, the second formant and the first formant. Phoneticians have dozens of these features. In fact, Allard Youngman quantified 24 different features for fricatives. We're going to call these the continuous cues. That's the critical thing. They're continuous. You can have a spectral peak anywhere you want. Here, this is a sh. It's around, I don't know, 2,700. For an S, it might go as high as 6,000. It's completely continuous. It can vary. So we can also think about these in 2 dimensions. So here I've plotted for an actual set of measurements, of actual set of frequencies, the spectral mean or the spectral peak on the x-axis, and the second formant frequency right here on the y. You can cluster, you can see the S's all have high spectral means, and the S's all have lows. So at one level, the way we have to encode speech is we have to come up with some kind of continuous acoustic space that really captures the gradiency, the messiness, the variability. So categorical perception starts from that. The idea is we're going to take our speech sound, we're going to encode it in some continuous, probably high dimensional auditory space. We're going to call that for today perception. Later on, that space gets carved into categories, like in this case, S or S. We're going to call that categorization or cognition. Now, Liberman's argument was that in order to discriminate 2 sounds, just to say if they're same or different, you don't need to label them. Identification is not necessary. So the argument then is that discrimination is assessing primarily this perceptual encoding level. And therefore, if we find differences in discrimination, it suggests that that sensory, that perceptual, that cue level is warped in some ways, that you're not hearing things the way they are. You're hearing things in a way that are biased by the categories you have in your language. So in a way, what we're talking about is a feedback effect. Now, there's lots of different mechanisms by which this could happen. This could be some kind of auditory discontinuity. This can be a learning effect. Gary Lupien has argued it's an actual interactivity in the system. There's a million mechanisms. I'm happy to discuss those at some point. But suffice to say, at the broadest level, what we're talking about is some kind of influence of cognition of categories on this continuous sensory encoding. So in a very simple way, we could think of, in this case, we've got the spectrum of the fricative going from S to S in continuous steps, and categorical perception says it's not sufficient to just put a boundary here, to just carve it up. Instead, the way you encode those cues is warped to align with the categories of the language. So if you start to think of it this way, categorical perception looks a little radical, right? It's not like other kinds of categories. It's not like the way we might conceptualize most conceptual categories, where it's just, okay, these are all dogs, these are all cats. You're literally seeing it differently because of that. Now, historically, the time, 1957, was a good time for categorical perception. It was sort of an idea whose time had come. Right at that moment, of course, the cognitive revolution was going on. In fact, that was the same year, I believe, as Chomsky's review of Skinner. And the cognitive revolution was built on a metaphor of the mind as a computer, that the mind processes things symbolically. And categorical perception gave us a great hook. It was that, hey, we have all this messy, continuous sensory information, but categorical perception can rapidly transduce that into a symbol. Now we're ready to go. Now all of the mind as computer metaphors start to work because we can do this really automatically. Now, the other reason that this was a good time for categorical perception was that inside of speech, people at Haskins, people at MIT, people at Brown had started to identify what we now call the problem of lack of invariance. These are spectrograms that were actually, they're on display at Haskins. I took this picture a few years ago. These are Al Liberman's original spectrograms where he literally recorded, I don't know who, saying kun, gun, dun, zun, sun, every possible context. And you look at these and you're like, wow, what is it that makes a ga? Look at how different all of these gas appear, right? This is the problem of lack of invariance. It's very hard to find features that correspond to speech sounds. And the reason for that is multiple. One is that the exact same value of a Q, for example, the same spectral mean for a fricative, could be consistent with multiple phonemes. Every Q is affected by multiple factors, things like talker, speaking rate, co-articulation, prosody, dialect, you name it. And the result is that there just isn't an easy one-to-one mapping. It's not possible to have a necessary and sufficient set of Qs or feature values that correspond to phonemes. Now, you can even see that here in the measurements I gave you. This is just 2 Qs for 2 phonemes, the spectral mean and the F2 frequency. And one of the things you see right off the bat is the amount of overlap. There's a large region in the middle of the space where sounds could be either S or Esh, and there's no way to tell. Now, categorical perception didn't solve that problem, but it does suggest the problem is solved somehow. That is, the fact that the input is warped suggests that the auditory system must have some way to pull apart the categories, right? And if categorization starts from this instead of this, the problem becomes a lot easier. So I see this as a sort of a testament that invariance is solved somehow. And at the time, we thought there might even be specialized mechanisms for speech that help solve it. Now, we now know that's not the case. Categorical perception, as I'll talk about, has been shown all over the mapping cognition. So it's clearly not a speech-specific solution. But the thought was this is a good solution. This is part of the solution for how listeners deal with all this variability. Now, this became a very compelling story. And in fact, it's spread. This is the number of new citations in a 5-year period since categorical perception was discovered in 1957. You know, there was 5,500 citations, 55, alone in 2015 to 2020. It just keeps climbing, right? This is an idea that just really people found compelling, and for all of these reasons. It spread to other speech contrasts. So the original Liberman paper looked at ba, da, ga, and very rapidly, people started to expand it. It spread to color vision. It spread to visual objects, face perception, music for expert musicians. Non-expert musicians don't show the effect. There was a paper recently, categorical perception of p-values. That's really clever. Line orientation, getting much lower level. It's big in neuroscience, both in speech and in non-speech. It's been shown in infants. It's been shown in animals listening to human speech. It's been shown in animals listening to conspecific sounds. It's been shown everywhere. In fact, I think it's still possible if you found some new domain and demonstrated categorical perception in, you'd still be able to publish that. It's just this thing, this principle that people have liked. Now, it's not just like cute, though. This is a big deal. And the reason is that in many of these domains, categorical perception has been linked to debates about modularity and domain specificity, for example, in face perception. It's been linked to debates about perceptual expertise, for example, in music perception, and about linguistic relativity, or the Whorfian hypothesis when it comes to color. And that's a great domain to look at this because different languages carve up the color continuum differently. This is a way of asking if you see things differently because of the language you speak. Here's the problem. Well, here's the problems. And this is really the core of the argument I want to make today. First of all, in speech, categorical perception is not actually that universal. And I think that's an issue that speech science needs to wrestle with. Second, we've known for quite a while that it's wrong about the nature of speech cue encoding. And I'm going to show you evidence of that today. But here's the subtler argument that I don't think the field has really wrestled with. Categorical perception as a model of speech categorization really emphasizes the wrong things about categorization for current models of speech perception. It was perfectly well suited to the models we had at the time, which were largely motor theory. But at this point, as we've moved to a much richer understanding of speech, it's emphasizing the wrong things. And it's, in fact, inconsistent with modern theories of speech. It's also inconsistent with things that we know listeners do with speech. So just the phenomenology of what people do with speech every day, it's hard to see how that fits with categorical perception. And lastly, I think, and this is really a little more speculative, that it's dangerous when we apply it to other domains of language, like development, speech and language disorders, and multilingualism. And I think overcommitting to a categorical model leads us down a path that may give us the wrong answers. So let's start with the simple one. It's not that universal. Well, okay, so I went through recently and looked for every speech perception paper I could find showing categorical perception. And we have a fairly nice, diverse set of things. I've found papers that do stop voicing. Of course, that was the original Liberman paper. That's ba da ga. Or sorry, stop voicing would be pan ba. Number of papers, many papers using voicing, many papers using place, ba da ga. There was some excellent work in the 70s on affricates versus fricatives. That'd be like cha versus sha. That was an interesting domain. And there's a couple of studies on laterals like L and R. And those have been really interesting because of cross-linguistic differences where some languages don't discriminate those, like Japanese and Korean. Those all show categorical perception. However, fricative place of articulation shows less categorical perception. And depending on who you ask, vowels show no categorical perception. And most papers on Mandarin tone don't show categorical perception. So there's some points against categorical perception in some areas. But I think the bigger point here is this is really just a small subset of the phonemes of language. People haven't tested approximants like wa and ya. There's been no test of non-sibilant fricatives like th and the. Voiced affricates, nasals, lots of manner distinctions, free voicing, as far as I know, non-English places of articulation, a uvular stop or a uvular fricative, not tested. The vast majority of phonemes have not been tested, and yet categorical perception is sort of claimed to be this thing, this organizing principle of speech perception. When some sounds don't show it, other sounds don't. And none of the theories of categorical perception are really prepared to deal with this kind of idiosyncrasy. Are stop consonants, which is really where most of the work done, really representative of all of speech perception? I'm not so sure. They actually differ in a number of really key ways from every other speech sound. What kind of theory would actually predict this? I'm also not so sure. But let's go back to these cases, fricatives, vowels, and tone. Remember that categorical perception was supposed to help solve the problem of lack of invariance, the variability that different talkers in different contexts have. But tones, vowels, and fricatives are the ones that show the most contextual variability. This graph, many of you will have seen before. This is from Hillenbrand, Getty, Clark, and Wheeler, which was a replication of Peterson and Barney, where they literally just measured the vowel formants of every possible person. They did like 10 men and 10 women and 10 children. And you can see immense overlap. Like if you needed the help of a pseudo-specialized mechanism to deal with invariance, why wouldn't you see it here where you need it the most? Voice onset time is actually fairly unambiguous and much less affected by contextual factors. So this kind of begs a question of like, well, okay, what is CP doing for us, right? Initially, it was thought to be part of the solution to lack of invariance. And yet here we're starting to see some challenges that maybe we don't need it. Maybe this isn't part of the solution, in which case, is it a spandrel in our theories? What's it really mean? All right, so that's the first step. It's not that universal. Second step is to go after and to think about seriously the empirical basis about the nature of speech cue encoding. So remember the original assumption that discrimination doesn't require labeling, and therefore it's affecting that first layer, that pre-categorical encoding of cues, of auditory whatever, right? Well, we could ask if this is right. Well, let's start with the classic tasks. Al Liberman and in many categorical perception papers use what we call the ABX task. I apologize for these tasks. They all have these names whose origins are lost in psychophysics, like ABX and 4AIX. I don't even entirely know where they come from. So you'll just have to bear with the names. But here's how the ABX task works. You're going to hear two sounds. One is the A sound and one is the B sound. And then you get an X sound that always matches A or always matches B. And you have to say which one it is. So for example, if the A sound was an S, that's step 5 on the continuum. The B sound was esh, that's step 3. And then you got S5 again. Your correct response is A. If the A sound was S with a step 6, B was S with a step 8, and then S with a step 8, your correct response is B. Now notice you don't actually have to label these, right? You just have to decide which one's a closer match. So this is in principle a judgment you could make entirely at the auditory or perceptual level. This is in principle a thing you could do even if you didn't know the language, right? I could give you sounds like ba, 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 right? And you would know the correct answer is A. I could give you anything. Now, the problem here that was pointed out first by Fujisaki, and later by Pizzoni, is that this task requires listeners to hold A and B in some kind of auditory memory. And not only that, you've got to protect A from interference by B. You're trying to hold two very similar sounds in memory. B is likely to interfere. So the system, the cognitive system, has to find a way to do this more effectively. Well, what's a durable way to maintain things in working memory? Some kind of category encoding. It's difficult to maintain fine-grained auditory stuff. Echoic memory has a very short duration. Phonological memory is durable. Let's replace it. The consequence, of course, then, is that this isn't categorical perception. It's just categorical memory. And I don't think that would surprise anybody. That's not a radical claim, that memory is well-suited and well-organized around categories in a way that it can't necessarily do for raw sensory input. And in fact, there's a whole history of really lovely work of attempting and succeeding in building less demanding discrimination tasks. Pizzoni and Lazarus developed the Fourier-IX task. Arlene Carney built an oddball task. And then later on, Bert Schouten and Ellen Gerritz and Arjun van Hessen developed what they call the 2IFC task, which is a variant of the Fourier-IX task. Again, I apologize for the tasks. And in each of these cases, you see less and less categorical perception. This figure here is really kind of tells the whole story. This is from one of Bert Schauten's last papers. You can see the dark line with the X's. This is the predicted categorical perception curve, or the predictive discrimination function from the identification. And you can see, yeah, there's a nice peak like there should be, right, at step 3, which was where the subject's boundary was. When you use the ABX task, the dotted line, you can see it matches the predictions pretty darn closely. But when you switch to 2IFC task, it's basically flat. Now notice it's not flat because people are failing. Actually, people have a pretty good D prime here, about 0.75. People are succeeding at discriminating it, but there's no hint of a peak whatsoever near the boundary when you switch the exact same stimulus to this 2IFC task. Now, outside of speech, actually, we do the same thing. This is a really lovely study by Debbie Robertson, who looked at color categorical perception. And they also noted the memory demands inherent in discrimination tasks. And so they used a sort of edge detection task, which has very minimal memory demands. And they used the JND, where you're actually making the colors closer and closer until people can't discriminate them anymore. So you're really going after this notion of precision. These are the English listeners. You can see their boundary between green and blue, and is right here sort of in the middle, but you can see there's no hint of a discrimination peak at that point. The Korean listeners actually have 3 categories. They have boundaries between 2.5 and 3.7 and 3.75 and 5. And again, you don't see any hints with the Korean listeners. All the evidence for categorical perception just vanishes when you switch to a less memory demanding task. So that's the first nail. The discrimination tasks appear to impose memory biases. Now, that doesn't make them any less interesting. I think discrimination is actually a really fascinating human behavior. It's really essential for perception, but it means they can't necessarily tell us about lower level perception. Now, this really culminated for me in an argument that David Pizzoni made in 1974 with Jeffrey Tash. He said, let's question the assumptions here. Liberman said, hey, you don't need labeling to do discrimination. But what if you used it anyways, right? What if discrimination just took whatever was available? Could be information at the continuous sensory level, could be category level. Well, let's work through the possibilities here. Let's pretend you're doing a within category discrimination where the difference in frication spectrum is 5,000 hertz. That's a very large difference. So, okay, when you hear those two sounds, you get 1 point favoring discrimination. There's clearly an auditory difference there, but they're both labeled the same. They're both esh. So you don't get a point there. On the other hand, for a between category discrimination between 6,000 and 6,500, now notice that's the same acoustic distance. You get a point for that, but those are different categories. Now you get 2 points. Basically, the point is, even if perceptual is vertical, even if every 500 hertz difference gives you 1 point in favor of discrimination, even under those assumptions, you should get a discrimination peak. You should see categorical perception. What that really then means is that the empirical phenomenon of categorical perception, the profile of discrimination, is also consistent with veridical perception, the exact opposite theory. Even if perception is not categorical, we should still see categorical perception. And this is part of what led Bert and Ellen and Arjun to argue that categorical perception has ended as we know it. So, okay, this still leaves open the question, right? Discrimination can't tell us one way or the other. Is it categorical or not? Both are consistent with the profiles we see. So you might ask if there's a better way to assess speech cue encoding. And Don Massaro and Jeff Cohen asked that in a really clever experiment back in the 80s. They said, let's actually have people rate, not just tell us if it's ba or pa, but rate how ba-like or pa-like it is. This has now become really popular. This is called the VAS, or the Visual Analog Scaling Task. Jan Edwards, Effie Capnula, and I, and Ben Munson and others have started using this extensively. It's really cool. You just tell people to rate wherever it is along the continuum. Now, what Massaro and Cohen said was, look, if people literally cannot hear the difference between steps in the middle of the continuum, if all they're hearing is ba or pa, what you ought to find is that as you move from step 1 up at the top to step 7 at the bottom, that just the distribution of responses changes. So at step 1, people are mostly choosing the left side of the visual analog scale. In step 4, they're choosing the left or the right, but they can't hear the stuff in the middle, so they never choose it. And at step 7, they choose only the right. Now, if people really were capable of hearing this fine-grained continuous stuff, what you ought to see instead is that the mean of their ratings kind of marches over. There's always going to be noise, of course, but their ratings are actually going to reflect the VOT at some level. This is what they found. As you can see, there's not a lot of evidence for the categorical model there. And in fact, they looked at 3 different continua and a number of subjects. They did individual model fits, and the results really support a continuous model for virtually everybody. Now, more recent work has gone to the brain. This was a study that my former student Joe Toscano and I did, and it was an accident. We actually weren't intending to look at this. We were looking at the P3, which is a late component that indexes categorization. But when we were squinting at our data, we also noticed that the N1 looked interesting. Now, the N1 is a negative deflection of the EEG wave that happens about 100 milliseconds after an auditory stimulus. It's generated in lower level auditory areas like Heschel's gyrus, which is where auditory cortex is, the superior temporal planum, those sorts of areas. And what Joe and Joel Denhart and I observed was that the N1 seems to show a very linear effective VOT. You can see here, I've just zoomed in on that one component. When the VOT is 0, so meaning it's a perfectly good ba, that's the purple curve, you get a very low N1. When it's 40, that's a perfectly good pa, you get a higher N1, and you can see all the steps in between. And we dug every which way into this data to see if there was any evidence for warping anywhere in the system, any evidence for individual averaging artifacts, and we couldn't find it. This has now been replicated. In fact, Joe did a wonderful study using optical imaging that gives you much better localization, sees the same thing. The point is, here's an index. This is an index that can actually tell us essentially what VOT, what voice onset time a person had. We can start to look at that sensory level, and we don't see anything discontinuous there. So if you just take at face value this claim that perception is influencing sensory encoding, we don't see a lot of evidence for it anymore. One, we know now that discrimination tasks can impose biases. That categorical perception could be observed even if perception is not categorical. And the handful of studies that have been able to directly assess this stuff at a lower level do look like some kind of linear encoding. So when we look with newer methods or just clearer eyes about our old methods, there's not a lot of evidence for the basic claim that categorical perception makes about speech perception. Now, this might actually be true in other domains, and I think Debbie Robertson's work in color suggests it very well could be, but no one's looked, and I think that's an important place where we need to investigate. All right, let's move on to the theoretical issues here. Categorical perception as a model of categorization really puts the emphasis on boundaries. It really says that the most important thing to represent is the boundary between categories. Now, that's not, you can argue about whether that's really what Lieberman meant. I'm not sure it is, but certainly that's been the takeaway in the field. And, of course, the boundary might be highly multidimensional, and the boundary is what matters. But the problem is that very few, if any, modern theories of categorization emphasize boundaries. I mean, Ashby does in the Covis model, in half of the Covis model. But most other models focus on things like prototypes or exemplars or schemas, connectionist or neural networks, simulation models, Bayesian models. None of these implement boundaries. Boundaries emerge in all of these, right? There's always a boundary between two categories. But the core job of the architecture isn't about representing a boundary, right? Categories are represented in other ways. And all of these models of categorization emphasize the within category or the internal structure. I mean, that was the real contribution of prototype theory when Roche came up with it, was that categories, common categories like common objects, have a prototype structure. There's an internal structure to the categories. Now, Joanne Miller, back in the late 80s, early 90s, noticed this and actually started looking at it. And she gave subjects tasks in which they would hear a ba or a pa, in this case it was a pa, from a long continuum, and they just had to rate, hey, is this a good pa or not? She was directly inspired by Roche's work. And you can see here actually that listeners have a really rich understanding of the structure of the pa category. They know that a VOT of 200 milliseconds in a slow rate of speech is not that great a pa, right? But a VOT of 80 is. You can see how the structures change with respect to context. People aren't just representing the boundary, they're representing the internal structure. Now, we've been referring to that as a sort of gradient category, and some work I did back in graduate school showed that actually this isn't just about phoneme categories. You can see the remnants of this all the way up at the lexical level. So after you recognize phonemes, you then have to access words. And we can measure how much you access words by using the visual world paradigm, which is a really simple technique where you hear a sound, like in this case, bear or pear, and you have to match it to the picture. And we monitor eye movements to see what you commit to along the way to making your decision. Are you fully committed to bear? Is that the only thing you looked at, or do you look a little bit at the pear? And what we see here is that if you manipulate, again, the speech from B to P using the speech continuum, that when the voice sense time is 0, so that's a good bear, they don't look very much at the pear, but they briefly do, and then they look away. But if you make the VOT 5 or 10 or 15, people increasingly look at the pear. So they're not trying to throw away this within category stuff. They're actually preserving it all the way up through the level of lexical processing. And here I've just plotted the area under the curve, and you can see, again, it looks really quite linear. As the VOT moves towards the boundary, people look more at the other object, and as the VOT moves away, they look less. Listeners are basically tracking how good of a ba or a pa a sound is. So you could ask where this comes from. Well, actually, Joanne Miller's first paper gives us hints. So here we have the same goodness ratings I showed you before about how good a ba or a pa is, in this case, fast speech, that's the open circles, or slow speech, the closed ones. And here's a histogram of actual VOTs from actual talkers. And focus on the black one, that's the pa category. And you can see that the shape of the histogram kind of matches the shape of the goodness rating. People are actually tracking the statistics of the input to decide how likely a sound is going to be a ba or a pa. So the first thing then is that CP seems to emphasize boundaries, even though categories are gradient. And this is, of course, consistent with a whole variety of different categorization architectures. And the gradiency is preserved pretty far up the processing chain. Now, I'm not arguing that this is proof against CP. It's not, actually, right? As long as categorical perception allows some within category sensitivity to emerge, you can get this kind of gradiency. But it also suggests an inconsistency with the paradigm. The goal of CP is to discard within category variation. And here we see something that's preserving it. So this is more about fitting categorical perception into the rest of speech and not necessarily, strict proof against it. And that's the next chapter here. So as I just showed you, listeners track how likely a sound is to be a ba or a pa, right? And we can see this in the goodness ratings. Why? Like, why do you want to know this? Why isn't it sufficient to just say, hey, that's a good ba or that's a good pa? Well, one answer that a number of people have explored is that this is actually helpful for coping with uncertainty. So, for example, this is a histogram of actual bas and pas, and you can see that the bas in green here generally have low voice sensor times, around 10 milliseconds, and the pas generally have higher ones, around 50 milliseconds. Now, if you were to get an 8 millisecond ba, given these statistics, you'd say, oh yeah, that's definitely a ba, I can commit. And if you were to get a 60 millisecond pa, you could be very certain that that's a pa and you shouldn't commit. However, in the middle, right, where it's still clearly on the ba side of the category, it might be helpful to hedge your bets. A voice onset time of 17 or 18, well, I'm going to go with ba for now, but let's keep my options open. Let's not commit all the way. And so one solution you might propose to the uncertainty here is that, well, you should make a gradient commitment that matches how likely a VOT really is a ba or a pa. Oops. Now, a fantastic study that Megan Clairds, who's here in Montreal or there in Montreal, did a few years ago, actually manipulated this. They actually changed over the course of the experiment whether VOTs are tightly clustered, that's the top, in the top graph, the sort of peaky distributions, or whether they're broad, right? Do you get a lot of variable VOTs? Do you live in an uncertain speech environment, maybe one featuring many different dialects or many different talkers? Or do you live in a very precise one? And then they measured people's categorization with both eye tracking and with response curves. And below is the predicted values. I couldn't find them on the same graph. But the idea, and this was shown in the data, is that when people encounter broader, wider categories, meaning more uncertainty, they become more gradient. They're actually responding to the uncertainty by keeping their options open. Does this matter? Does this help? Well, one way to ask is to mislead people. So this is an older study I did where we gave them words like barricade and parakeet. Now, those words are kind of unique. We found a bunch like them, where if you got an ambiguous sound at the beginning and made the wrong inference, you wouldn't know it for a while. For example, if you heard barricade and thought you heard bee, you'd commit to barricade and you wouldn't get any information to tell you that it wasn't barricade until a couple hundred milliseconds later when eat arrived. Now, if the system was categorical, this would be bad, right? You've committed to barricade, you're building evidence for barricade. Suddenly you have to switch gears and move to parakeet. That's tough. On the other hand, a gradient system could keep both options open. And then when the extra information comes in, it could much more flexibly recover. So we tested that in an eye tracking paradigm. This looks to the correct object. So if they heard barricade, this looks to the parakeet. As the voice onset time went from 0, which was a good barricade, to 35, which is a poor parakeet. And you can see that the same kind of gradient recovery holds. People are making a partial commitment. And then if that commitment needs to be revised, that's a lot easier if they kept their options open in the green regions of these curves than if they didn't keep their options open in the purple region of the curves. McCall Sarrett, a graduate student of mine, looked at this with ERPs, and she actually did this very clever analysis where we gave people sentences with different voice onset times in it, and we can, of course, quantify the N1. But what she did is every 2 milliseconds, she ran a regression to say, hey, how much of that gradiency is preserved at this moment in the ERP? And that's shown here in the red blobs. The red blobs show you when you see the gradiency, and you can see the red blobs are significant all the way out to 900 milliseconds. People aren't just briefly entertaining this gradiency. People are actually preserving it for quite a while, and they're doing it alongside things like sentence processing, which is the orange blobs. So why is it then helpful to be non-categorical? Well, one answer is it helps you cope with uncertainty. Another answer is it helps you integrate information to make decisions and deal with contextual variability. Now, what do I mean by that? Well, if we can't count on categorical perception to solve the problem of lack of invariance, how do listeners do it? Well, modern theories of speech perception from a number of different avenues all agree on a couple of things. One, use lots of information. Don't put all your eggs in one basket. And use some sort of combination, some kind of probabilistic combination, whether you're using the fuzzy logical model or a Bayesian model or some kind of logistic regression, a prototype model. They all say combine it probabilistically, weigh the evidence. I did this about a decade ago with Allard Youngman. He had almost 3,000 recordings of the 8 fricatives of English from 20 different talkers, 6 different vowels, and he had measured 24 cues to each token. So we could actually implement this assumption, and we did. And we found that when we did that, we could actually classify fricatives pretty well. We could do about, I don't know, 80, 83% correct. However, listeners were getting 91% correct, and that was actually a little surprising. We measured everything you could possibly think of to measure, and we used an optimal statistical classifier. So like, why are we not getting 91% correct? Well, one thing we noted is it's not enough to just measure more cues. Let's say we have a spectral mean that's a little lower than it should be for an S. Well, the reason it's a little lower is that the tongue is in the wrong position, and that's going to affect all the other cues. So all we're doing is adding redundant information that's capturing the same variability we're trying to overcome. The real question to ask is like, why is that tongue too far back? Maybe it's because there's a back vowel coming up. Maybe it's because that's that speaker's dialect. And in fact, we know this. Every cue that we could measure is affected by other factors. The frication is affected by the vowel. It's affected by the talker. It's affected by speaking rate. So instead, what we need to do is come up with a way to account for all that, to factor it in. And we used a really simple model based on linear regression. We took each cue value and said, hey, is this higher or lower than I would expect for this talker, for this context, and so forth? And you can see the raw cues over here, lots of overlap, lots of variability. Once I've done that, the 2 categories just pop right out. This is essentially a generative model, though it wasn't implemented in any sophisticated way. But here's the difference. Categorical perception says our goal as listeners is to ignore irrelevant variation. I want to filter that out, try to ignore the talker, try to ignore the co-articulation. This approach, I need to explain it. I need to account for it. Very much like the way a psychometrician might have multiple individual differences factors that we're going to pull out in order to see the thing you might really care about. And when we do that, this model now matches listeners' performance. So here you can see the green is completely overlapping with the white. And the right graph is the error patterns in front of different vowels. And you can see we also match that. Now think about that for a second. Here's how that works. Let's imagine we're coding fundamental frequency, which is not a very great cue for voicing. The mean F0 in our sample for a voice sound is 148 hertz. The mean F0 for a voiceless sound is 160. And we got large variation, plus or minus 40 hertz. Now I get a VOT an F0 of 154. That's kind of ambiguous. I don't know what it is. But I know it came from me. And I have a pretty high F0 at 130. So actually, it's 14 hertz higher than you would expect. It's very clearly a voiceless sound. That's all we're doing here. It's nothing special. Relative to me, this is an unambiguously voiceless sound. Now, the critical insight here is you can't do this if you don't code the fundamental frequency continuously. If you just warp it and say, oh, all of these are within category, all of these are within category, you're just going to add noise. If you impose categorical perception on these measurements, it makes it more difficult to solve this problem. So the gradient story marshals a lot of force here. Empirically, I've shown you non-categorical discrimination, linear cue encoding, and a gradient prototype structure. And theoretically, it makes for a more flexible perceiver, and it enables listeners to more sensitively account for variance. All right. Lastly, because I'm going to skip the applied domains, this is inconsistent with what listeners do with speech. The real problem is that categorical perception doesn't make sense in a bigger picture. CP was developed in ways that resemble a beads on a string model, where you get a segment of speech and you make a signal decision, and then you need to identify that segment and move on. But that's not how speech works. This was first identified by Paul Mermelstein. He noticed that, hey, the length of the vowel is a cue for multiple things. So take a word like bad, it's got a nice long vowel. And if I say bad, I get a shorter one. That's a great cue for which vowel you're hearing. However, bat also has a shorter vowel. The vowel length also tells you about the voicing of the final sound. And of course, bet has an even shorter vowel, right? So you can't just do one thing with vowel length. You've got to do 2 things with it at least. And he actually built a simple model of this. If you warp your perception of vowel length for the vowel decision, you've just lost information you need for the consonant decision. Similarly, Terry Neary and Doug Whalen and Roll Smits pointed out the same thing in fricatives. You can have a spectrum of ship here that's nice and low, and sip is nice and high, but soup is in between. Now, soup is in between because there's a rounded vowel coming up. Again, if we warped the frication cues and said, oh, I'm only going to pay attention to differences that signal ship versus sip, I've just lost information about the upcoming vowel that we know people can use. And in fact, it's worse than just phonemes. Like, sure, we have to identify whether it's S or S or E versus U, but we also have to identify who spoke it. We also have to identify their state of voice, their state of mind, their emotional state, what dialect they spoke, what maybe they have an accent from a second language learner. All of this uses the exact same cues. And so if you're focusing just on S versus S, maybe categorical perception makes a lot of sense. But once you warp the signal to support one decision, you've lost information that could support these other decisions. Now, for years, in fact, I was talking to Ben Munson, he was like, yeah, sociolinguists knew this. If you had to assume categorical perception, you'd never be able to get any work done. You'd have thrown away all the information that we care about. So this is not news to a lot of people who work in sociolinguistics, but it's a point that's very well made for people who work in speech perception. Now, this is a problem outside of speech. Think about face perception. What are all the different things we do with faces? We code their identity, we code attractiveness, we code emotional state, we might code group membership or racial identity. And the same cues contribute to all of them. So for example, eyebrow height, if you look at these pictures, is a pretty good cue for distinguishing me and Stephen. It's also a pretty good cue for distinguishing surprise, right? If I categorically code eyebrow height to get identity, I'm going to lose my ability to recognize facial emotion. And in fact, these principles have been in some ways embodied in what David Leopold calls norm-based face coding, which is pretty much the same operations as that relative cue encoding model. And he uses it to think about categories, attractiveness, etc. This is also true with color. In color perception, all of the work is on our ability to name colors. This is yellow. But what else do we do with colors? We use it to recognize objects. But notice that that's not a canonical yellow. It looks yellow because it's a banana, but it's actually kind of a tan. Here's some number 2 pencils that are actually orange. Yellow is a critical feature for identifying both of those, but not the categorical version. We also use it for social signaling. At Iowa, we all wear this ridiculous color. We call it gold, but it's really orange, right? And if you got it wrong, you'd look like you were rooting for the other team, right? So really fine-grained stuff matters. We use it for judging food. Every time you go to the grocery store and you pick out your bananas that are ripe, right? Or the bread that's a little darker, right? You're making very fine-grained judgments. Now, very few of these everyday cognitive tasks require us to use canonical yellow. All of them require viewers to recognize and use fine-grained differences. And the same fine-grained differences must be used in different ways for different goals. Like the degree to which it's on the orangey side really matters if I care about whether I'm rooting for Iowa or Purdue. The degree to which it's on the green side really matters on whether my bananas are ripe or not. And so again, if we were just to warp our perception of color to support naming, we might be cutting ourselves off at the knees to do all this other useful stuff that we do with color. So CP is inconsistent with what we know about speech. Everything must be used to support more than one decision. And categorical perception warps the basis of these decisions in a way that is biased by only one. It's really hard to see how you can implement categorical perception in a system that's now making multiple decisions at the same time. All right, I'm going to skip development. We can come back if people are interested. And I want to move on to some bigger picture conclusions. First thing, what I showed you today is that categorical perception is wrong empirically. It's not universal. It may be a special case in speech perception. Discrimination does not assess that perceptual level that categorical perception is supposed to assess. Categorical perception is guaranteed from discrimination tasks, even if perception is continuous, and more direct estimates of perception are linear. And when this approach has been applied to other domains like color, we actually see the same thing. I think the bigger point here, though, is that this is undesirable theoretically. It emphasizes discrete boundaries, not gradient categories. It makes it harder for people to be flexible. It makes it harder for people to deal with context, and it makes it harder to get more than one thing out of the same cue or segment. Perception is continuous, and it should be. Categories are gradient, and that's useful. Now, you probably are thinking, have I set up a straw man? Am I holding categorical perception to an impossible standard? You know, many people have said, hey, but oh, yeah, no one said people couldn't discriminate within categories as long as they discriminate less, right? Or gradient perception is totally consistent with weaker forms of CP. Or this is my favorite, no one has ever argued or shown true categorical perception, just these kind of partial ways. All of that is true. I'm not arguing for that strong version. I want to take on this first point, though, because Al Liberman did. This is the second categorical perception paper. In this first paragraph, he says, indeed, the discrimination was relatively so good across the boundaries and so poor within the boundaries as to suggest that subjects could only respond to these sounds categorically as phonemes and could hear no other differences among them. So this isn't crazy. This isn't a straw man. And in fact, Bert Schouten showed nearly perfect categorical perception more recently, right? This is that paper I showed you at the beginning. When you use the ABX task, the data lines up almost perfectly on top of the predictions. So yes, true categorical perception, the hardest form of it, is in fact possible. But it's not generally shown. Generally, we see a weaker version. And yeah, a weaker version of CP is possible. But do we really want to hold on to it? As I argued, it's very hard to falsify it because of the Pizzoni and Tash approach. True non-categorical perception has in fact been shown by Massaro and Cohen, by Joe Toscano, by Robertson, Hanley, and Pack. And it doesn't seem to add anything to our theories or fit with our broader thinking and perception. So why do we want to hold on to this concept? So where did the field of speech perception, and here I'm talking about myself, go wrong? Could we have been a little more obvious to all the other people who've worked in categorical perception? You might argue, yes. I mean, if you look at some of the early papers, it's sort of a little squishy, categorical and non-categorical modes. Arlene Carney got a little more direct, non-categorical perception of stop consonants differing in VOT. But Robert Crowder really nailed it. Categorical perception of speech, a largely dead horse, surpassingly well kicked. This was published in 1989. And of course, Bert Schouten just ended it, right? So it's not like we're really hiding this fact. Right. In fact, the first paper I wrote on this, people said, why are you even doing this? Everybody knows categorical perception is done. It sent me these papers to read. And yet, there aren't really very many or any comprehensive and critical reviews written for a general audience. Most psycholinguistics and phonetics textbooks still teach it. And we let others, even within our own field, perpetuate it. In my view, Pizzoni and Tash undercut what we call the derivation chain for categorical perception. This was a term coined by Paul Meehl, a philosopher of science and a clinical psychologist, that describes the chain of logic, theory, and assumptions that links a hypothesis to the predicted result. Later on, Oberauer and Stefan Lewandowski called this part of the theory crisis. The idea is that there's a whole theoretical set of assumptions that let us take discrimination and map it to perception. Pizzoni and Tash showed us that that chain doesn't really hold, but we, in my field, failed to take that derivation chain seriously. We failed to hold ourselves and other people accountable for it, and we failed to communicate that to other fields. So what's the future? Well, one, should we just throw out all that data? No. We actually can make very clear conclusions when we observe CP. Under the Pizzoni and Tash model, we aren't going to conclude that there's perceptual warping, but there must be some robust categorization that can infect discrimination, that can help organize things in memory. So as a marker of strong categorization, this is useful. We clearly need to be a little more critical with other fields and a little more analytical with our own. I don't think we can just accept ABX tasks and identification curves at face value. This applies to textbooks and review chapters, categorical perception in other fields. Hanley and Robinson have a great review in Psychonomic Bulletin that addresses this in faces and color. But even within speech, we need to be a little more critical of their analysis of CP and claims. I think we also need to think about new measures. I've shown you ERPs and eye tracking. I think that's not what you need, though. I mean, those are great, but they're hard and they're expensive. Even something as simple as a visual analog scale can do it. And Effie Kapnula and I, as well as my current students, Ethan Kutlu and Samantha Chu, have been using this to look at all sorts of interesting individual differences using a continuous scale. And we've uncovered things like the noise, the trial by trial noise may be predictive of things like development or disorders. So even something as simple as a continuous scale can help. I'm not arguing either for a completely bottom-up system. What I'm arguing for is that categorical perception says there's a specific top-down interaction here that results in information loss. We need an interactive system that uses knowledge, that uses expectations in a way that preserves fine-grained detail, not discards it. And categorical perception is a barrier to that. I'm also not arguing that people don't categorize. Categorization is at the core of speech perception. In fact, Andrew Lotto and Laurie Holt make a lovely argument for this in the current direction papers. What I am arguing is that it's not clear that categorical perception should be at the core of speech perception anymore. Thank you.
Okay. Can you hear me?
I sure can.
Okay. Thanks very much. And we've arrived at the question and answer period. I just want to take, and we have questions. I just want to take the chairman's prerogative to ask the first one. And I don't think you'll have time to answer it, so I just want to put it on the floor. You have been discussing categorical perception at its true origins. That's where the word was invented, in the context of speech perception and in the context of speech continua. So there were two specific features there. It was speech and it was continuous. There's a third one. I mean, nobody declared themselves on it from speech perception, but I don't know what the assumption was. But it could be that these categorical perception, putative categorical perception effects in speech continua, it could be that they were caused by learning effects, or it could be that they were inborn. So that was uncommitted, okay? My question is, a lot of what you said applies still very much to speech. I mean, what we're going to do in speech is discriminate and so on. How does it apply to an area that is unlike speech perception in every one of those respects? It doesn't involve continua. It doesn't involve speech. It doesn't. What it involves, however, is stimuli, and stimuli are, of course, they have features, and so you see or hear or taste or smell things that come to your senses. They have multiple features, but the features are not necessarily, in fact, often not at all, ranked along a continuum. It's not a boundary question. It's a classification question. And as soon as you bring learning into it, you have a timeline, which means there's a time before you learn a category and the time after you learn the category, and everything in between. There, many of the measures that you referred to, ABX discriminability, similarity judgment, which is an important one, ratings of similarity, and the ERP measures, all of those seem to change as you go along that line from being at 0% performance to when you get to the point where you've learned the category, you got it. Yes, you've got a name there, but it's not like deciding between ba and da along a continuum. It's just categorizing. How much of what you've said applies to that much more general context?
That's a wonderful question, Stephen. And I don't know. I mean, there's a level in which you might even want to question whether the concept of categorical perception applies to that general context. Because at that point, if you take sort of a Rob Goldstone-y approach, right? People are extracting features from the stimulus, right? They don't know the features going into a learning experiment like that. Those features are being learned. And you're right, they're not continuous in the sense that there's not continuous variation between feature value A and feature value B. It's more like, is feature value A present, right? Is feature B present or absent? In that case, it's not clear to me entirely that the CP paradigm, it's an empirical paradigm, you can apply it, but it's not clear if it means much, right? Because there's not a clear sense of what is the perceptual encoding as opposed to what are higher order features, right? I mean, at some point, what you're calling a feature, I might actually call a cognitive level representation. And so I think that requires some thought. I think what you might measure with a graded similarity judgment there or discrimination task is actually something quite different than what Lieberman was talking about when he was measuring that with an ABX task in speech. Oh, hey, there's Rob. They just raised his hand. Perfect. And so like that's where I have to wonder whether maybe the concept is being stretched a little far. But Rob's going to tell me I'm wrong now, and I want to hear what he has to say.
Okay, you're on, Rob.
No, I'm not. So I thought this was really provocative, Bob. Really cool stuff. I agree with a lot of it. I guess one kind of question I have is sort of in the context of prediction involved in perception. I mean, so a lot of it, I'm not sure about this strong division between memory and perception. And I think a lot of the situations in which we're memorizing something according to these phonetic categories, there's something kind of like that going on, even when the thing is right there in front of you. I guess I'm thinking more visually than auditory. But I guess along with this also, I'm thinking of situations where it's useful to investigate the stimulus in one way if you begin to get an idea along one category versus another category. So you kind of raise the great question of why would you want to bias the incoming stream of information? Why would you want to warp that instead of just treating it as continuous level information? And I guess part of my answer to that might be it's useful, like, as an analogy, if you think that your stimulus is going to be on the left side of the screen, you might want to look preferentially to the left side rather than the right side, and vice versa. And I feel like that happens for lots of stimulus cues, that you begin to think that it's something, and that might usefully bias your search for future diagnostic information, exactly bearing on that leaning that you have.
That was an awesome question. And I think you're right, but I think that's not categorical perception. So here's the argument. First of all, I think this predictive approach is a really elegant way to think about it. And in some ways, when Allard and I developed the model of recoding things according to what you know, oh, it's this talker, it's this gender, that was a predictive model. It's very similar to a predictive coding framework in terms of using the difference. So very much in the spirit of top-down effects, prediction being a major one, and that's majorly useful. However, none of that actually, even though you are saying, look, I know this pitch is too high for this guy, so it must be voiced, I'm not then just ignoring that, right? I'm actually using it, I'm harnessing it in the spirit of a generative model. That's not the same as categorical perception. Categorical perception, the space just shrinks, right? Here, the space is getting parceled out, right? It's not to say that everything matters and you're coding everything equally like you might in an exemplar style model, right? And it's not to say that you have to have this massive high dimensional input. You do have to have selective attention to certain dimensions. You do have to have top-down guidance of what Q values are important. But that's far more sophisticated than what we talk about when we talk about categorical perception of like, oh, it's yellow, let's ignore these differences in the wavelength, right? And I think we need to be moving towards a more sophisticated view. I'm not sure that categorical perception helps us that. I mean, we might be better just to like sort of say, yes, there are these kinds of effects that are important. Let's not call them that anymore, so we can be a little more open-minded about all the other varieties of ways you can get it, because I think this is a term that's just sort of mired in an erroneous history.
Okay, while we wait for are there other questions that are ready to pop up now? Let me.
There's a couple of magic hands up.
I don't see them.
Oh, Frederick, maybe?
Yeah, why don't you call it? I only see a few.
Yes. Hi. Thank you so much for the talk. That was really interesting. You partly answered my question. But from your presentation, I have the feeling too that categorical perception was some kind of functional hypothesis at the time that got refined, that we made dynamical and more fine-grained through the years. And I wonder if now the results really are to simply understand in this way that we could still make some use of this idea, of this functional idea of categorical perception, or whether there are some bigger implications for understanding cognition in general and for the future of cognitive science in general too.
Wow,
because it's really an important concept at the core of cognitive science, categorical perception in general.
Maybe this is partly what Rob was complaining about too, right? Like, I'm going to completely agree with you, Frederick, in the sense that like, categorization is core to cognitive science. We have no cognitive science without categorization. We have no speech. We have no vision. Like, right? We just live in the blooming, buzzing confusion. Categorical perception, when it was developed, was a particular type of interaction between perception and categories. And I feel like as a field, we kind of want to save it by continuing to add new things and enrich it to where it's sort of lost its spirit, right? Its original spirit was specialized mechanisms that rapidly abstract motor gestures and ignore things that are irrelevant for categorizing speech sounds. We're way past that now. So I just don't know if I see the advantage of like hanging on to it and continuing to redefine it. I think we have way better metaphors to talk about categorization. Predictive coding metaphors are much better. For example, Bayesian information integration metaphors are much richer, right? And so, I mean, I guess what I'm almost calling for is a little bit of a we just can't keep moving this one idea. Oh no, now it's this. Oh no, now it's this. Oh no, now it's this. And all of the thises are right? We're making progress, we're making headway, but at some point we should take this sort of Kuhnian paradigm shift approach and say, oh, you know what, we've pushed that idea a little further than it should go, and we need some new metaphors to think about cognitive science. And I think there are good ones out there. I didn't even actually propose any good ones. I just went after the old ones, but I think there are much better and there's much smarter people out there than me that have better metaphors for us to be using. But are all built on the and this is how it works now, and this is how it works now. I think we just need to untether them from the past.
Andrea?
Yes, thank you. It was a wonderful talk. I've been lately thinking a lot about the Ganong effect, and I've been actually working on an experiment where we have a BOT continuum that goes from a real word puppy to a non-word buppy. And people just throw their categories away. Like they hear puppy like way, way, way beyond what we think is like a really good bee. So that just makes me think, in the real world where we hear real words, how useful is thinking about phoneme perception when we have all of these very rich cues that give us like all of this information, and whether you think this continuous approach to perception of phonemes ties in better with what we actually have in the real world beyond discriminating minimal pairs, which like is kind of rare, I guess.
Yeah, really rare. I think it's a great question. I've done work on the Ganong effect. If you guys don't know, it's the way that lexical information can kind of override phonetic input in many cases. And I think you're right. I mean, that illustrates like if listeners really were making a very hard and fast decision about the category, the Ganong effect wouldn't be able to override it in that way. I don't think it means we shouldn't study speech categorization. I think actually it can teach us a lot about cognition in general. And of course, your ability to identify puppy, even though maybe the initial sound wasn't that important, some constellation of the other sounds were to get there, right? And so it's not like that's irrelevant, but we do need to think about how this fits into word recognition, which is why we started using the visual world paradigm, and to sentence recognition and discourse. Sarah Braunschmidt and Joe Toscano actually have some great studies looking at that. And I think you're probably right. Like maybe speech perception doesn't have to do it all. Maybe we have to get close enough, right? In the spirit of like Fernando Ferrera's good enough sentence processing. And this may be true in other areas of cognition as well. As long as you can get enough information to push forward to the next level, the redundancy there, the idiosyncrasies there can help you sort it out. And the best way to do that then is to not make strong commitments at the earlier level. Keep your options open and use like whatever you have available, whether it's additional cues, knowledge of how a talker sounds, knowledge of what the discourse expectations are. So I think that's a really great point.
That's super interesting. Thank you so much.
And now from Southampton, Christoph Wetzel.
Good evening, Christoph.
Hi, Bob. Thanks a lot. That was amazing. And there are a lot of parallels with color vision. So I should say I have done a lot of research on categorical perception and color. And I had always the suspicion you get the same problems with speech and phoneme perception as we get in color. And your talk is basically confirming that suspicion. So I'm very happy. What we also find is that in color, you get these categorical effects in memory, very robust, shown in many, many studies. So that's very nice. And I would like to raise two points. The first one is the question of what is the continuous reference to which we compare the categorical effects, right? So I don't know about speech perception, but in color, I can say the way we sense wavelength of light is not continuous, right? Our cones, it's not linear. Our cones, they don't respond in a linear way. And it happens that, there is a very non-linear development of sensitivity across wavelength to light. So we do have these dips, these troughs and peaks. They do not correspond with the categorical distinctions, except for one, blue and green, which has been used extensively in this field. And so when you measure discrimination thresholds, what you find this very nice dip for discrimination thresholds for blue and green, because they're exactly where the L-M mechanism is. So L and M are long and medium wavelength cones, right? So that's the cone opponent axis, second stage of processing, but you don't find it anywhere else. So you don't find it for the other categories. And then the other thing is, so then the question is basically, first question I have to you as an expert in speech perception, is it possible you get something similar in speech where, you basically, the way we sense, voice onset time or something has also troughs in discernibility and sensitivity that could be entangled with tests of categorical perception, where you get them at incidentally at some places, but then when you would look at the broader range, as you suggested, has not been done very thoroughly, that if you look at the broader range, then suddenly you realize, well, that's an incidence because of the way we sense the physical world. So that would be, the first question to you.
Well, it's a wonderful question. One of the popular theories of categorical perception in the 70s and 80s was sort of what they called innate perceptual discontinuities. And there was some evidence for that in place of articulation in voice onset time. Like you said, it's happenstance, and some languages might seem to take advantage of it and others do not, right? And so it's not a unifying account, but maybe that's okay, right? I would also be the first to say that no speech cue is linear. Frequency, for example, is log scaled. Duration is log scaled. So even at that level, we're making assumptions when we linearize something in a continuum. So I mean, I think that's completely right. What it does, and actually I hadn't really thought of it in this framework before you asked this question, Chris, so I really appreciate it. Is it, okay, maybe some of these discontinuities are there, but they're no longer explanatory for language. They're just something the perceptual system has to deal with in order to align itself with the ambient language, just the same way that vision does. Like maybe, your language doesn't carve green and blue there. You're going to have to overcome that. Maybe perceptual learning can, right? Like in the sense of like Vernier hyperacuity, where you can learn these really fine-grained things. Maybe not, but it's more of a problem language has to overcome than a solution of one of these problems of languages, I think, in the way you're describing it. And I find that to be kind of interesting and compelling. Did you have a second question? It sounded like you might.
I did. I just didn't want to continue talking all the time. So the other point is that, we had the study where we then equated colors in discernibility. And then we tested whether people would have a categorical effects with these very, empirically equated colors. And what we found is that the guys with whom we measured discrimination thresholds, they didn't have the category effects, but only those who were completely new to the task. So it seemed that those who were highly trained to do this discrimination task, they would kind of focus on very fine-grained differences and they wouldn't get this category effects, but then you get some naive people. And I think here I'm connecting a bit to what Robert just said before, right? That they would kind of assume they would have to look at these differences, so to say. They would pay attention to the difference they're used to in everyday life. And then they would get this kind of response time and accuracy, you know, a bit higher accuracy across the boundary, a bit faster at the category boundary, just because they would pay attention to that difference.
Yeah, the task would kind of push them into it. I would love to see that paper, Christoph, if you don't mind. That looks, that's really an interesting paradigm.
Yeah, I mean, yeah, I'm happy to discuss with you maybe a bit further later on, because I think it would be interesting to pull these two, you know, your approach into phoneme perception and color a bit together and, you know, make something a bit broad out of it. That would be interesting.
Yeah, that would be really interesting. And I love this idea of generalizing from like psychophysical observers to naive. Like that's a very cool paradigm. So let's maybe talk offline about that a little bit.
Okay, we're coming close to the end of the time, but I want to, before we end, I want to see whether there are people from music perception, pitch perception, or from neural modeling, neural net modeling of category learning and representation who have anything that they want to discuss with Bob.
I have a whole story on music I didn't tell, so I'd be happy to talk about music in particular.
Well, if there are no takers, and we're soon going to run out of time anyway, I want to take you back again, sort of the chairman's prerogative, to the timeline, the learning timeline that from which I see all of this. Try to imagine yourself the way I do. For me, the main placeholders for what a category is are the words in a dictionary. Every single word for which we have a name, that's a noun, a verb, or an adjective, is the name of a category. Very, very few of those lie along a continuum. Very few of those are innate. However, they all have given that they're not innate, they all have this timeline, which is there's a time when you don't know the category, and there's a time when you do know the category. By knowing, you can say which is which. If the initial state is a confusability matrix in which you have all kinds of stuff with all kinds of features, and you have no idea what's what. And if you told somebody to categorize, all they could do would be like sorting cards. It would be ad lib and improvise. There is, in the case of categorization for the dictionary, a right or a wrong of the matter. You get it right or you get it wrong. Well, just speak about it in terms of the simplest possible case, member or non-member of a category that has a lexical item. And before you know what the name of it is, you don't know anything. You can still test discriminability. And what you'll find, and by the way, the emphasis in the kind of work on category learning that I do is not on discriminating within categories. It's in discriminating between categories. That's what's absent at the beginning of that timeline and present at the end. I asked the same question I did before. When you go back to the speech examples or the color examples, you're going back to continua and so forth. In this world, where we have before and after, and we have categories that are more confusable before, less confusable before, and then you have after, where all of them, at least the emphasis is on between category description, all of them, you find heightened discriminability between categories. Do you think that that's also a version of categorical perception that it's going down the drain with?
I guess I'll take a strong temporary view that yes, but in the sense that when we do those discrimination tasks before they've done any learning, all they have access to is the continuous perceptual representation, whatever that is, right? Whatever bundle of features.
You're imagining the wrong thing. I'm not looking at Baz versus Daz.
No, I know you are. Imagine you're looking at Gabor patches or Greebles, right?
Yeah, I'm Google showing everything in my image.
Yeah, but at some point it comes into the eyeballs, right? And there is a representation that you have that you can use to rate discriminability or similarity. And that's all you have before you've done any learning. Is that fair?
What if, yes, but what if I'm doing with them before I start the learning or talking about categories? I simply look at discriminability.
Sure. And you can measure that. That's gonna be the sort of baseline, right? After learning, discriminability is gonna go up enormously, right?
Between categories. Between
categories. And I guess what I'm wondering is, in this domain, when discriminability goes up, does that really mean that the sort of perceptual organization has changed? Or does it now mean you have access to a second level of representation to help you with discriminability, which is the category labels? I mean, that's the essence of Pizzoni's model. It's like you have this other thing now. And before you did any learning, you didn't have that thing. And so that's the sort of straw man. That's the thing you have to rule out if you really want to show that this is an example of categorical perception. Now, there may be great ways to rule that out, but most of the cognitive psychological tasks we use don't isolate a single level of analysis, right? We can't say, hey, I want you to only attend to it at the sensory level or this perceptual level and ignore the labels. We can't do that. Now, people like David Leopold do that in faces using adaptation effects. That's a really cool way to do it, is to look at the way adaptation works. That's unlikely to be biased at the higher level, right? Although maybe it is, I don't know. We did it with ERPs in speech, right? But I think that's the issue, is that the kinds of similarity and discrimination tasks that we use don't isolate a single level of analysis. And if you want to make a strong claim like categorical perception, you need to. If you don't want to make a strong claim about categorical perception, that's fine, right? People are getting better in these interesting lawful ways because of interesting lawful responses to experience, because of perceptual organization in the environment. Those are actually the real questions, like not whether it's categorical or not, in my view. But I think if you want to claim categorical perception, you've got to first rule out the Pizzoni and Tash model. You have to be able to say, yeah, even when categories are not involved in this judgment, the perception has changed. And I do think there are ways to do that, but it requires, really careful thought and sophisticated experimentation.
I don't think the Pizzoni model applies at all to what I was describing. I mean, somehow it drags back the same questions, the same old questions from speech categorical perception, and applies it here where they don't. Let me try to say it in English, and then we'll have to, I'll listen to your answer, then we have to call it up. Before you learn the category, you have more trouble telling apart instances of members and non-members than afterwards. That's all. All we're asking is, can you tell them apart better once you've learned the category than before you knew the category? And the answer is you can. And that's perception. It's not something else. And it's not the Pizzoni model.
I wouldn't say that that's necessarily categorical perception.
Okay. Well,
right. I think
we can retire the term.
And that's kind of what I'm arguing for is that, yeah, that's a true fact, right? You can tell them apart, but categorical perception implies the perception is biased by the categories. I don't know that that necessarily constitutes strong proof of that. It could, right? But I think we have to know.
Okay, with that, I want to thank you for an extremely, sorry, Christoph has another point, yes?
No, but if the time's over, it's also fine. I mean, I wanted to say something about uncertainty and the role of uncertainty in all this, but we can also have a discussion later if you want to finish up.
I think uncertainty is a critical point, and we can definitely talk about that later. Like that is a good argument for this, is that is coping with that. But we'll talk about that later.
Okay, I want to thank you very much for coming here to Montreal and much for coming.
Stephen, thank you for inviting me. This was lots of fun, and I've really enjoyed the debate.